one more. Let's see. Yeah. Yeah, I believe everybody now is here now. Unless there are more people since the last seminar. Oops, wait. I need to fix something. Check. The camera is off now. And then maybe we can bring this screen down. Okay. Let's see. Yeah, it's working. Okay, everybody, let's start. I believe everybody's here. We have even one more person online, I think. Okay, so this is day 2 of our series of seminars. Okay, I hope we managed to do everything okay today because it's a lot of material. But so I have first some initial things. So I received some of the home assignments, but not from everybody, I believe, because it was like 5 or 6. So I believe half of the class delivered the home assignments. It's very important, okay, to do this home assignment because you practice the concepts that we learned during the class, and it's very important to make this. Okay, so today we are going to discuss the solution to the home assignment, computational complexity, some basic stuffs about quantum mechanics. Then we are going to introduce qubits instead of bits. This is when the magic starts, right? So we are going to enter really into quantum systems and how to make quantum computation with them, right? Here we are going to have the first introduction to this first quantum gate, the Hadamard quantum gate. I hope all these materials can be seen today. If not, we continue on the next seminar. All right. So today is day 2, right? And we will have 2 weeks of stop, and then we continue supposedly on 16th of May, right? Okay, so what about the home assignment last time? I hope all of you easily did this. If not, let's discuss this now, right? So the problem was to explain this circuit gate by gate, what these gates were doing with these bits, and supposedly this gate should add numbers. So I gave you a series of bits A, let's say AN until A0, and then I give you a series of bits B, which goes from BN to B0, right? So this could be, for instance, this could be like 1, 1, 1 plus 1, 1. I want to sum these two zeros, right? So this circuit here, apparently it will give you the sum of each digit. So SI will be the sum of AI plus BI plus the carryover from the previous pair of digits. Okay, and then it would, this sum would also produce a carry out to the next pair of digits. So this is CI plus 1, right? So this is the next sum, and it would appear here. Okay, so let's move on. What about this? So at least me, what I decided to do, I decided to explain this by parts. Okay, so first I'm going to talk about the sum itself. So this operations plus the carry out from the previous set. Okay, and then we go for the other part of the circuit. Okay, here it's a simple one because we only have this exclusive OR gate, this one and this one, and we just need to consider two situations. For example, when you're summing the first time when I equal to 0, you know, for example, when you have 111, I'm going again and again from this example, 111 plus 111. When you're summing these two numbers, in the first column, you don't have carry out. So by definition, carry out here is 0. Okay, so this can be the case that we are going to consider when CI equal to 0. So the carry out from the previous summation is 0. Then the sum in this case reduces to AI plus BI. Of course, I mean, I say plus, but what really means is exclusive OR, right? In this case, when the second, let's say the second guy here in this leg, in this second operator here, when this guy is 0, we have this case and we have this case. So when these two guys are zeros, you just have that if A is 0, the result is 0. If A is 1, the result is 1. So this becomes just the trivial gate, right? So we don't need to think in the case when the carry out was 0, you don't need to consider this gate. This gate becomes trivial. And then the result from this first gate will go straight to the sum. Okay? So we just need to consider this guy. And then this is obvious, right? This is XOR. XOR means that if A equal to B, the sum will be 0. They have to be different for the sum to be non-zero, right? Again, let's consider, again, let's go back to this example, 111 plus 11. When these two bits are the same, you put here 0. You don't put 1, right? And then 1 becomes the carryover. So this 0 here is exactly the result of this gate here, okay? Exclusive OR. So it's this digit will only be 0 if both AI and BI are 0, or if both AI and BI are 1. If one of them, if they are opposite, 0 and 1, this becomes 1. So this digit here should be 1 instead, right? So this is first situation solved. And then if the carryover from the previous summations, if this is 1, then now we have to consider these two cases here. One and 1, right? So if these two guys is 1, so when A is 0, the result should be 1, and when A is 1, the result should be 0. So this means that actually it becomes a NOT gate. Okay, so when Ci equal to 1, this is the case we are considering now, this becomes a NOT gate, right? This will become this little gate here, right? Okay, then what is the situation? If now, okay, this is the NOT gate that I represented. This means that if A equal to B, the sum will become 1, because this guy here gives the exclusive OR, right? So what is the negation of exclusive OR? It will be 1, 0, 0, 1. So if A and B are equal, which is these two cases, then it will give sum equal to 1. If A equal to B are different, which is these two cases here, then it means this guy will be, the sum will be 0. Okay, so this is the situation for the carry out. So let's go now for the next stuff, next part of the calculation. The previous part was for the sum. Now we are going for the carry out. Okay, so the carry out, now it's more complicated. It's given in terms of the AND gate, again exclusive OR, and OR gate. So let's see, again we are going to make these considerations. If this Ci equal to 0, then this second gate, now we are going to consider this entrance here, right? So we copy and bring here. If Ci equal to 0, the second AND gate produces always 0. So this is the case when this guy is 0 and when this guy is 0. This gate here will be 0, and this gate, this in this case will give 1. So doesn't matter what is the result of this gate. The result will come here will be always 0. Okay, so, and if this guy is 0, and the last in the OR gate, so we have this case 0 and 0. When A is 0 gets 0. When A is 1 gets 1. So this guy becomes the trivial gate, right? So in this case, we just need to consider this end here. And now, if A equals B equals 1, this will be the case where the carryover will be 1. Otherwise, the carryover will be 0, which is expected. This is exactly what we know from the summation algorithm, right? Then there is a situation when Ci equal to 1. So when Ci equal to 1, it means that this leg that comes here, this is 1. If this is 1, then this gate, the AND gate here, you have this situation when the second leg is 1. This guy is 1, this guy is 1. So 0 becomes 0, 1 becomes 1. So this gate here becomes the identity gate. This guy becomes trivial, right? If this guy becomes the identity gate, now we have the combination of these three gates, and XOR and OR, right? So I decided to, how did I explain what would happen here? I just took the definitions, transformed this into an equation. So transforming this into the equation, you would have this, by the way, using this concept we use in the last seminar, right? So we learned how each one of these entries can be turned into some kind of equation, right? So this is the effect. This first gate here, this AND gate, becomes this. And the result from this gate, XOR, becomes this part. And they both will produce, since this is the trivial gate, they both will be entering here in this OR gate. So this OR gate means this here. And then we just have this turning this into an equation. So the OR gate, the equation is 1 plus B minus AB times B. So this is the term. And then putting this into evidence, we have simply this equation. So the idea now is to check all the values for AI and BI, right? Let's see if I did this in another slide. No, I did it here. Yes. Yeah. So the idea is just to check. The idea will be that you will put AI equal to 1, AI equal to 0, and check one by one what would happen with this result here. Okay. But this is as simplified as you can get into all these situations. Okay. All right. Another point is that on the last seminar, I promised an example, but I in the end I forgot to put this. So I put here. I promised an example of implementation of a logic gate. So one of these examples can be the NAND gate, the not AND, right? So for example, this is the table of the gate. And indeed, your bit will be a voltage. So when you have voltage 0, this is bit 0. When you have the voltage non-zero, this is bit 1. Okay. So for example, let's go here. You will put your input will be voltages in B, will be voltages in A. This circuit will work like this. You will have a transistor 1 and transistor 2. Okay. And then your current, it will try to go from here to here. If it has a voltage here, last seminar we saw how transistor behave, right? So if you have voltage here on this third end, the current can go. If you don't have voltage here, the current is blocked, right? So you immediately see that if you have voltage, if B is different from 0, if you have voltage in A, so if A equal to 0, this is the case where current will flow in these two legs of the transistors, and then it will go here with voltage 0, right? So we know that here voltage equal to 0. So then the measure, let's say there is some apparatus here that measures voltage. So it will immediately measure the lowest voltage in the circuit, voltage equal to 0. In the other case, if you have either A or B equal to 0, or both of them equal to 0, the point is that you will block current either here in this end of transistor or here in this other end of transistor. And it means that the only way current will flow in your system will be through this source. So it will be voltage and then going here. Okay. And then this gives exactly this table, which is the NAND gate. Okay. What is the NAND gate? If A or B, if both of them are 0, if one of them are 0, both of them are 0 is this case. If one of them is 0 is these two cases, right? If this thing happens, what you're going to have? You're going to have a voltage in your measure, in your apparatus here that measures voltage. And that will give bit 1. But there's a special case when you have both of these guys with voltage, A and B. There are voltage here. It means that the current will flow here. And then what you're going to have? You're going to have 0 voltage in your system, right? So your apparatus here will measure V equal to 0. And it will give result 0. So this is one of the examples of logic gates. You can store information in the bits A, and you can store information in the bits B, right? And then from these two informations here, it will go through a logic gate, and then in the end, you can have either results 0 or 1, right? So this is one of the implementations, possible implementations. You can do this even at home. This with a proto board, you can practice this with these NAND gates. I don't know who likes electronics can do this. Okay. Now let's move on. I think this was more or less a big review of last last seminar, some kind of remembering of what we were working there. And now we will try to move on with our materials. Can please someone please remind me what time I have a break? We have to stop, because I checked in the web page and the timetable is not working. Now it's working. Yeah, so 12:30, right? 12:30 is when we stop. So I have a good hour to discuss this stuff. Okay, I will try to be not too long, but try to cover as much as possible because it's a lot of information. So computational complexity, right? To solve some problem, now we are going to go to try to make some theory about the process of solving some problems computationally, right? So going back to Alan Turing, going back to these concepts where you are concerned more if something is possible or not possible. I will try to touch on some concepts here, and you will see that there is a very important practical application. I think maybe one of the most important practical applications. That is the problem of safety, digital safety. Okay, let's go. So to solve any given problem, a certain amount of resources is necessary. So you need resources to do this stuff, right? For instance, to run an algorithm on a computer, you need space, memory, right? Time and energy. You need space itself because the computer has some volume, right? In the times of Alan Turing, you needed rooms for computers, right? This was huge machines. But also memory here, he means also that space can be some number of transistors in your memory, right? As we saw in the last seminar. So you need space, time, and energy. So these three, one of the most fundamental physical concepts, right? Space, time, and energy. And computational complexity is the study of the resources required to solve computational problems. So this topic that we are going to discuss now. Sometimes it is immediately obvious if one problem is easier to solve than another. Let's check what about this. In other cases, it may be very difficult to evaluate and measure the complexity of a problem. This is a particularly important objective which affects many fields from computer science to mathematics, physics, biology, medicine, economics, even social sciences. So I guess this includes most of us that are here in this group, right? The point is that, for example, in my computer simulations that I do, I have many parameters, and based on these parameters, my solutions there, my computations there, can take longer, can take less time, and it's very tough. It's very tough to limit myself in the set of parameters that it's doable. Because there sometimes if you put some weird parameters there, the simulations can just take too much time, right? So an important task of computational complexity is to find the minimum resources required to solve a given problem with the best possible algorithm. So it means optimization, right? So since the moment when you start writing your code, you sometimes can optimize and make your code faster, but also you can buy new machines, more powerful, smaller machines, right? Even cheaper machines. For example, with Bitcoin, there is all this trade-off between power of the machines, how much energy they consume, they consume. So everything counts, right? The algorithm that you're going to use. Anyway, just to give an example. Even simpler example, I think we already touched these cases before. So consider these two algorithms we learned at school, right? Adding, multiplying two numbers with roughly the same number of digits. So adding, I show here how to add two numbers, right? And you see that in the algorithm, you sum column by column, right? You can put, sometimes there is this carry out that goes to the next line. But the idea is that you do column by column, right? So If the number of algorithms is n, you see that in the summing algorithm, in the addition, this is done column by column, column by column, like this, until the end, right? So this is proportional to the number of digits in your numbers. Okay, so we say that this is proportional to n, or we say that this is order n. Okay, this O here is of order n, right? For multiplication, this is a little bit more tricky, right? Because we do one number times each of one digit times all the digits from the previous number, and then we sum with the next number times all the digits of the previous number. So there is a combination of all these digits there. Actually, this crosses between the columns, right? So it's not like summing. In summing, you have the same columns. So this is just proportional to n. In this case, you need to touch all the different columns. Each number multiplies by different columns. So in this case here, for example, the multiplication algorithm gives something proportional to the number of digits squared. We say order of n squared. Okay, so this is very interesting here, that depending on the algorithm, depending on what you want to do with these two numbers, it will of course give you different amount of trouble. You will have a lot of trouble to do this stuff or not, depending if how your algorithm scales with the number of digits in your numbers, right? So this means that in general, multiplying two numbers is more complicated than adding them. But is it really? Such a conclusion would be based on particular algorithms for computing addition and multiplications. Those the ones we discuss now is those learned in primary school, but could be different. So could there be different algorithms that lead to this different conclusion? Maybe, you know. So up to this day, nobody found a faster algorithm to multiply two numbers. The word here is fast. Nobody found a fast algorithm to multiply two numbers comparable to the simplicity of adding them. So up to now, nobody found an algorithm to multiply that it's order n. So far, nobody found this. Maybe one of you will find one day. I don't know if some of you goes to deep mathematics or computation. But so far, the best algorithm known was found by this guy, Sean Hag, in 1971, and he used fast Fourier transforms. So using fast Fourier transforms, he reduced from order n squared, he reduced this to order n log of n log of the log of n. Okay, I even did the plots for you guys. So this is the plots that represent the scaling of the number of digits in this here. It's n, and this axis, and this is all these functions. Okay, so this is if you have the function n, of course this is just a straight line. If you have n log of n, this will give this green line, and if you have n squared, you will have this parabola, you know. So good question. The log here is base 10 in this case. Okay, log here is base 10. So it means that this function here, n times log of n, log of n, this gives much slower increasing than n squared. So fast Fourier transforms, these are very powerful algorithms to multiply large numbers. Okay. What else? The thing is that still, this line here costs a lot. Even this line here, when these numbers start to increase more and more and more, if we neglect this curve from the plot, still this guy will win by a lot. So still the complication of multiplying two numbers is still much larger than just the complication to add them. Okay. Okay, I think this is interesting result. I see that you guys are excited about this. Very nice. I didn't know if it would be sound obvious to you guys, but I guess this is not obvious, right? Based on the algorithms. So the main distinction made in theory of computational complexity is between problems that can be solved using polynomial versus exponential resources. So there is even classes of algorithms that the complications grow exponentially, you know. So more precisely, if again n is the size, the number of digits, right, the input size, the number of bits required to specify the input, we may divide solvable problems in two cases, two classes, right? There will be a class of problem that can be solved using resources that are bounded by a polynomial in n. So polynomial, I mean n, right? N squared, n cubed, right? These kind of things, or log, right? N log, tarara, tarara. We say that these problems can be solved efficiently, okay? Or they are easy, right? Tractable, feasible. All of this is kind of synonyms. Addition and multiplication belongs to this class, but there are problems requiring resources that are super polynomial. The super polynomial, because of this super, you already know. I work with in a field called superconductors. So you already know that someone is trying to catch your attention when he calls something super. And super polynomial, it means that it grows faster than any polynomial in n. These problems are considered difficult, intractable, unfeasible, and so on, right? As hard as hell, and so on. So it is believed, this field is very open questions. There are lots of open questions still. It is believed but not proven that the problem of finding the prime factors of an integer number is in this class, which means that the best known algorithm for solving this problem is super polynomial in the input size n, in this number of digits, right? We cannot exclude that a polynomial algorithm might exist, but we don't know. So again, what is the problem? Problem of finding the prime factors of integer number. For example, you guys know that I didn't put a slide about this because I guess everybody knows what is prime numbers. Prime numbers is the number divided by itself and only itself and one, of course, right? So two, prime number, of obvious one, three, right? 5, 7, right? 11, 13. Only two delitelium. What is this? Only one in itself. Yeah, yeah. Uh, so 2, 3, 5, 7, 11, 13. You know, from the very beginning that there is no even prime number except for 2, right? They even call 2 sometimes a false prime number. 2, 3, I think they call false prime number or something. And these are the good ones from 5 on. But anyway, so these are prime numbers. And there is a very interesting task. If I give you any number, let's say I give you a number 14, can you find all the prime numbers that I can factorize this number? So the idea is that you will have to test all the numbers smaller than 14, or at least from half of 14, and check which ones produce it, right? So you would check like 14, does it divide 2, right? Yes, divides 2, right? Gives 7. And then you already get another prime number. So you already know that 14 is given in terms of 2 primes, 2 times 7, right? If I give you, I don't know, 9, right? So 9, this is 3, divides the prime number that it gives is 3. 2, it doesn't divide 2, 3. It's 3 by 3, right? Let's put like this. If I divide by 3, I get a 3. So it means that 9 is given by 3 squared, and so on. So I want what are the prime factors of each number. So expressing any number in terms of its prime factors. This is what we call super polynomial problem. Because the point is that you will need to divide this number by all the numbers before it. So this is pretty hard algorithm, because division, right? It's some kind of operation also between digits and so on. So you will always this will grow exponentially, probably, as we are going to see. You will see how this problem grows. But just remember that dividing a number in prime factors gives this scaling. So the scaling is exponential of something of the order like this, n to 1/3 log n to 2/3. So exponential here. If something grows exponentially with the number of digits, it means that, by the way, this is estimation, right? They did estimations about this. It's not exact. By the way, in this case here, n is the log of the number integer. It's not the number of digits. Okay, don't confuse. Okay, so let's say we call this n small here the log of the integer number, and then dividing this integer number n into prime factors will be exponentially growing in the number of operations that you need to do. Okay. For example, they did this estimation. This is old estimation with computers from 1998. Okay, but believe me that up to now, this has not improved so far. So the factorization of a number with 250 digits would take 10 million years on this computer that can make 2 million instructions per second. Okay. At that time, this was cutting-edge computer, right? And nowadays, what we do? Nowadays, because we have stronger computers, what you do is you just increase this number of digits, and also you will get some absurd number, like millions of years, right? To factorize a number. So therefore, we may conclude that the problem in practice is impossible, because I will not live 10 million years. I don't know about you. But in my case, I will not live like this, and then it's practically impossible to solve, right? From the algorithms that we know nowadays. Maybe in the future, someone will develop some of these algorithms, okay? But in our case, no, we are not going to do. We don't know yet, okay? Let's talk about this complexity classes, okay? So, by the way, you will see that this factorization, I showed this example because of some very important case, okay? So, complexity cases. We say that a problem belongs to the computational class P. This is very famous. Maybe if someone read the literature before of this stuff, you will see that this P and P will appear everywhere. So, this belongs to computational class P if it can be solved in polynomial time. Which means in a number of steps that is polynomial in the input side, in the number of digits, right? The computational class NP, instead, is defined as the class of problems which solution can be verified in a polynomial time, which is different, One thing is I give you an algorithm and you solve this algorithm. So I give you a question. What are the prime factors of the number 1,23758, right? This it will take you a lot of time to do this problem. But if I give you the solution, can you verify that that is indeed the solution to the problem? So if you can verify that in polynomial time, it means you are on NP class. Okay? Is it clear, this distinction? I hope I'm not destroying anything. I hope everything will go okay. All right, so one thing is to solve the problem itself. One thing is, once I give you the solution, you verify the solution, right? So intuitively speaking, finding the solution is slower than verifying, right? Sometimes even in chess, you have very complicated situation in the board. If I give you the best move, you will say, ah, yes, of course, it's very easy to verify that that is the best solution. Sometimes it's not so simple, right? Sometimes you need to say, why is this the best move? Because of this, because of that, blah, 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 blah. You need to make the analysis, right? And also in algorithms, you ask me what are the prime factors of a huge number, and I give you the solution. You will have to divide that number, but all those prime factors that I'm going to give you. So then you will take a lot of time dividing all these numbers. So these things scale with the number of digits, right? So this is the NP class. NP class is when you can verify solutions in polynomial time. Okay. It is clear that P is a subset of NP. So, namely, P is part of NP. So the number that, as we saw, right, as we analyzed that finding the solution is slower than verifying the solution. If a problem, if you can verify a solution in polynomial time, it means that you will solve that also in polynomial time, right? Is it clear? This thing, this part here. P is a subset of NP. I hope it's okay. Questions so far? I didn't stop for questions. If you guys have any questions about this, I guess it's clear. Tell more about P different from NP. Yeah, different from NP. This is we will speak exactly now about that. It is a fundamental open problem. So nobody proved. The question is not, we know that P is part of NP, but we don't know if P is equal to NP. The question is, are they the same class of problems? So if you have a solution that you can do in polynomial time. If you have a solution that you can do in polynomial time, can you check the solution also in polynomial time? And also for any algorithm, if you can check a solution in any polynomial time, can you find that solution in polynomial time as well? So that's the equivalent, right? That's the big question. I think there is a prize for this. If this was the case, there would be problems hard to solve, but whose solution could be easily checked, right? If P is not P. There is this hypothesis that P is different from NP, which means that there would be problems hard to solve. So it would take a lot of time to find the solutions. Could be even super polynomial. But the solution, once you know the solution, this could be easily checked, right? For instance, the integer factoring problem in the class is in the class NP. Okay. So if I give you the factoring, the prime factors of an integer, and you want to check that, this can be done in polynomial time. But as we saw before, finding this prime factors, this could be exponential time. It would be super polynomial, right? So it is easy to check if a number 771 is a prime factor of integer n, but we do not know if any algorithm that efficiently computes the prime factors of n on a classical computer. So once I give you prime factor, you can check that very simply. But I give you any number and you need to check these prime factors. It's not the same and can be much harder, right? So therefore, it's conjectured that the integer factoring problem does not belong to the class P. Also, nobody proved this. It's also conjecture. So finding the prime integers of a number does not belong to class P. It means that it's not on polynomial time, but it's on super polynomial time. This is a hard problem, right? Okay. So we say that a problem in NP is NP complete if any problem in NP is polynomial reducible to it. This means that given an NPC problem, NPC not NPC in video games, but NP complete, right? For any problem in NP, there is a mapping that can be computed with polynomial resources that maps into the map it to the NPC problem. So basically, the NPC is if there is this mapping that can, let's say you have some problem that in principle you don't know exactly what is going on there, you don't know the solution, but if you can establish a map between that algorithm into an algorithm that you know this is in polynomial time, it grows in polynomial time. If there is this direct map, this is called NP complete, right? Therefore, if an algorithm is capable of efficiently solving an NPC problem is discovered, then we should conclude that P equals NP. So you'll be able always to map these complicated, these unknown problems in principle. You'll be able to map that into a simple problem and then solve the simple problem and use that Rexec problem. Yes, there are many famous. This is one of them. I think I had somewhere. I know I closed this page. I had somewhere here some famous problems. This is one of them. There is also the traveling salesman. So you have many cities, and you have the distances between these cities, right? And I give you some. You know all these distances, okay? And where all the cities are. I give you some distance d. Is this distance d the smaller distance that you can run all the cities? So it's a problem of optimization. He wants to optimize the travel to go through all these cities. You know, this problem has application also in the aviation. For example, some companies they have these airplanes, and these airplanes are going around the country. For example, for Russia, this is very important, right? Huge country. So you want to optimize the network where your airplanes travel throughout the country. You have a limited number of airplanes, so it's not like you will fly to some place and discard the airplane. It has to go back. It has to go to other places. So how do you optimize this network of flights? This is a very complicated problem, by the way. And nowadays they use quantum computers to solve this problem, because with classical computer this takes arbitrarily long time, and now we found a mechanism how to do this in short time, like minutes. Some problem that would take millions of years can be solved in minutes with but I am going ahead of what I wanted to talk. Okay, so this complexity problem can be either way. You know, if P equals NP, then it's the same set, right? So all these problems they are equivalent. So it means that these two sets are equivalent. You can map one problem to another. So everything is done on polynomial time, finding the solutions and checking the solutions. But there is the point also where there are some problems where you can find the solution in polynomial time. There will be problems that checking the solution you can be done in polynomial time, but not finding the solution. So there will be guys here, some examples of algorithms here, which are to solve them. This is exponential time, but to check the solutions, this is polynomial time. And then if you can map these problems into some polynomial time, you will be able to find these complete guys here. There are can be either this way, either this way. Okay. So yeah, I put here. The Clay Mathematics Institute is offering $1 million reward to anyone who demonstrates that either P equals NP or P equals NP P different from NP. Okay, whoever wants to be rich can do this. By the way, oh, sorry, not printing. Next, I'm going to talk about why are we talking about this problem, right? Because there are protocols that use exactly factorization of prime numbers. So maybe some of you guys knew, but it's always nice to mention this, that there is this protocols in internet, in security of internet. This is, for example, very traditional one, secure remote password, SRP. Okay, so for example, when you want to log in some servers of a bank, something that needs to be very private, it has to be some factors of large number to because you will need a password to log into the bank, right? And we are going to use the fact that factorizing large numbers take very, very long times. So in simple words, the user and the bank server, they share the same large prime number, let's say Q, okay? This number with many digits, okay? Hundreds, even thousands of digits, okay? When you send your password to the bank, of course you will type this 6-digit password, I don't know, 4-digit password. You're going to type this on your phone. And then your phone will have the same number Q as the bank, this very large prime number. It will multiply your password by the prime number, and then you're going to send to the bank the full product of these two numbers. So what happens? What happens is that in the middle of the way, if there is some guy in a midpoint of internet, if this guy somehow he puts his hands on this number that you send, if this was just your password, what would happen? He would have immediately the password of your bank account. But if he gets this very large prime number, he will have to factorize this number and discover which of these prime numbers, which of these factors is your password. So it means that doesn't matter. He will take millions of years with the computers that we have now. It would take for him millions of years to find this, so it's practically impossible, right? So this is what happens in this. Basically, this is what happens in these traditional bank apps that we have. Of course, nowadays there is facial recognition. They will start putting more and more layers of security because cell phones can be hacked. People can steal your phone, right? With smartphones now, previously was a computer that you have at home, but now with smartphone, you can lose your smartphone. You can be drunk and someone use a finger or something, and then third person might steal you, right? So security in first place. Banks spend a lot of money on this stuff. Okay. Yeah. So this is pretty much what I explained, right? So this slide we don't need. So if this bank use six-digit password, the bank know and I know my password. So you will log in, send my password, and then there he will just divide the big factor, the big prime number, by the result that you send, and he will get your password, and then he will confirm, okay, this is really Tiago. Any question? Did I explain this okay, guys? This is um, some interesting mechanism that I would like to for you guys to know. Yeah. As we saw, this means that this would take millions of years for a person to steal your password. The problem is, if someone or some organization finds a method to significantly reduce the complexity of factorizing a number, then these types of remote security protocols would become useless. And this is the danger, So if someone, because as we saw before, this is all conjectures. So people say like this would take arbitrarily large time. This will take arbitrarily large time with the algorithms that we know so far. But nobody proved that there won't be a new algorithm that simplifies this stuff. So there are many studies on number theory that deal with this stuff to prove that there is algorithms or there is not algorithm. They want a clear solution for this. So far, nobody knows. So basically, we live in all our security online. We live under a world that maybe maybe someone can find an algorithm to reduce from super polynomial time to polynomial time, slow, make this factorization into prime numbers. A simple problem, and then he will know your password. Second point is, even using complicated algorithms, but using a much powerful computer with computational power huge, for example, a quantum computer, this could be also the case. It could factorize prime numbers using quantum computers, using very powerful computers. So this is what people suspect, that might be some class of quantum computers that has such a strong computational power that it can attack these internet protocols. And if this happened also, if these two situations happen, it will be nightmare, because you never know when and where these hackers will attack. If some Chinese guy, some, I don't know, some American guy, some Russian guy, whoever, some Iranian guy, whoever has hands on this stuff, he will immediately be able to attack banking systems of institutions. This is pretty exciting moment, because history is happening in front of us. We are watching history. It's a very privileged time to see this stuff. Okay, guys, probably I will start now, because from 12:30 we still have something like 15 minutes. Yeah, I will start discussing the basics of quantum mechanics, because now this is a division in the seminar where we are going to make a review of these basics concepts of quantum mechanics. And from now on, I hope we can start talking about quantum computation, not classical anymore. So far what we have seen was about classical computers, and now we actually begin talking about quantum mechanics and so on, right? This review will be short review, but I guess I will try to explain from big detail about the most important parts of quantum mechanics, okay? Beginning with the Stern-Gerlach experiment. Did you see this with Alexei Vagov? Did you see this experiment? I guess not. Yes. Oh, you saw this stuff with Alexei. Okay, very good, because then means I can go faster over this stuff. So before going to this stuff, I will use this concept in electromagnetism. In physics, we define this stuff, but here I just want you guys to get the basic intuition, the basic concepts here. Okay, so first we are going to use the notion of magnetic moment. So magnetic moment. Okay, guys, wait a second. Let me answer this. All right, I'm sorry, guys. Let's continue, right? So we use the notion of magnetic moment. Okay, we are going to talk about spins. So to talk about spins, I would like to explain a little bit about magnetic moments. Okay, so for example, when we have a circuit and there's electric current going around this circuit. You know, when there's electric current I going around this circuit, what happens? What happens is that there will be a magnetic field perpendicular to this plane of the rotation here. Okay, so let's write here B, right? But the point is that if these loops are very small, loops of currents, this is very small, we can define very important character of this system. It's called the magnetic moment. We call this mu. Okay, so it's proportional current that is circulating, and it's proportional to the area, this little area that is going around. And in principle, you can calculate the magnetic moment of some body, some physical body, by doing little by little these circuits, checking which current is rotating there, multiplying by this little area, and then you sum all these magnetic moments, and you get the total magnetic moment of your body. For example, our planet, the planet Earth, it has a huge magnetic moment because the magma is rotating, and this thing rotating there, this is basically some electric currents rotating, and then you have this magnetic field of the Earth, so you can have a compass and see where is north, you know. So that's macroscopic, that's very big example of magnetic moment. But also materials in general, you can reduce until you go to atomic level, and still there will be electrons rotating in the atoms, and you will have these magnetic moments there. Okay, even you can go even lower and go to one particle. You can go to electron, something that is just a fundamental particle, you know, and try to extend this concept to electrons. But as we are going to see here, some quantum effects appear, and then nature goes wild. Okay, so let's go for it for next slide. This is here the relation between the magnetic moment and magnetic field. So the magnetic, I put here this sketch here. Those interested can read more in this book. Okay, Introduction to Electrodynamics by David Griffiths. But the point is that, let's say I have ideal dipole. You go to the very smallest level. You know, if you have a magnetic moment pointing in this direction, magnetic moment mu pointing in this direction, then the magnetic field will be given by the component of magnetic moment in such direction times this direction minus the magnetic moment. There is this factor 3 also. So if you have, again, right, if you have magnetic moment mu, just one constant vector, and you do this product here, you will see that it will have a magnetic field. So these field lines here, these are field lines of a magnetic moment. So if you go to very small detail, in reality, if you have a big loop of current, if this is a loop like this, and there is a current here, again, there is area, right? And you multiply current versus the area, and you should have this magnetic field also. But it looks, one is like the limit of the other. You know, if you make the radius of this circle smaller and smaller and smaller, what eventually you get is the field of the dipole. So this is some kind of idealization of the ideal dipole, right? And this is the magnetic field. And as we know, magnetic fields, they can repel or can attract to each other. So magnets, right? If you are on the North Pole or if you are on the South Pole, they can attract each other. For example, here in this magnetic dipole, you see because of the field lines, this is magnetic moment mu. And in the magnetic field, what happens? The field lines go into the South Pole of the magnet, and they go out in the North Pole of the magnet. So basically, every magnet, it has some kind of analogous with the dipole. You know, let's say you have this standard magnets like this, north and south. All the field lines start on north, go down to south. Start on north, go down to south, right? something like this. So yeah, basically this is what I mean by magnetic moment. In the extreme case of a fundamental particle like an electron, we can think of its magnetic moment as if it was spinning around itself like a basketball. Okay? But we are going to see that the possible rotation states of an electron are completely unexpected. So again, because this is an electric particle, if it rotates, it will look like a current. There's current going around, right? So let's say I have an electron here. If this thing is spinning like a basketball, if this thing is spinning, maybe there would be some current also going around, some area going around, and then we would have some magnetic moment of the electron, right? And these two guys, Stern and Geller, they decided to check what are the states of rotation of the electron, right? So let's go for the Stern-Geller apparatus. A beam of neutral atoms, in the case they used silver atoms. So silver atoms, it has one electron in the last layer. So one electron. So pretty much what we measure here will be the states of rotation of this last atom, last electron, okay, valence layer, because this is most out layer, and the electrons inside they are shielded by this guy outside. Okay, and we introduce this magnetic field that this has to happen. It changes in space. It becomes stronger or weaker in space. Okay, when we send this gas of silver atoms, so they just boiled silver to a very hot temperature, and these silver atoms were going out here. And in principle, these silver atoms very hot, what happens? They can have any state of rotation. They could be launched, rotating in any direction with any speed, right? So what happens is that these atoms, they should have magnetic moment, any value of magnetic moment. So they observe basically what happened in the perpendicular direction to the trajectory. So they check that part of these atoms went up, part of the atoms went down. I'm sorry to repeat this part with Alexei, but it's because this is very important for the next stuff that we are doing. Okay. So at the entrance to the region with magnetic field gradient, the magnetic moments of the atoms are distributed isotropically, right? So basically, it was random, completely random atoms going out with any state of velocity, any state of rotation, and so on. According to classical mechanics, all values of magnetic moment between, let's say, minus m to plus m, so some minimum and maximum, right, are allowed. So as a consequence, the impact points of the atoms on the screen should be distributed continuously around the incoming direction with maximum positive and negative deflections corresponding to the values of maximum magnetic moment and minimum magnetic moment. If the force, basically what I say is, if the force here is, this gradient is constant. So this gradient here is given by this very large apparatus that produces magnetic field, this B. Okay, and now we have to see how the magnetic field created by these little atoms will interact with this other magnetic field. So the point is that we are going to check have a continuous value of magnetic moments. They should touch here this wall in a continuous way. Random values of rotation. So these magnetic moments could have any value, right? We would have all fields with electrons here. But in reality, what we found? What we found is that these values are discrete. Nature gave us big surprise. The experimental results are in clear contradiction with our predictions. Wait, maybe I skipped some important stuff. No, yes. They are in clear contradiction with these predictions. Only a finite number of spots are registered on the screen. In the case of silver, it's only 2. So these spots are equally spaced along Z and contained within the interval between the maximum positive and negative deflection. Deflected. Okay. In some cases, for instance, when using silver atoms, that was the case. There were only 2 spots on the screen. Okay. This apparently mysterious phenomenon found its explanation in the fact that electrons possesses um, intrinsic angular momentum known as spin. So it's not an actual rotation, the electrons, but it's actually something fundamental, some fundamental number for the electron there. And it's intrinsic, and they call this the spin. So the magnetic moment of the atom is proportional to its angular momentum, and for atoms like silver, the angular momentum is simply equal to the spin of the outer electron, the electron outside. The 2 spots on the screen correspond to the 2 allowed spin states with respect to a given direction, which may be labeled as spin up and spin down. The experimentally determined values of the spin angular momentum are given by these 2. When they measured what should be the angular momentum, they found that it should be plus 1/2 times h bar and minus 1/2 times h bar. By h bar, we mean the Planck's constant. So there are 2 definitions. You can define h um, like this, 6.626 times 10 to minus 34 joules per second. Or you can divide by 2 pi and get h bar. Okay, if you divide this number here by 2 pi, you get h bar. So in this case, what they measured there was half of h bar, right? They found half of these values. This can be the magnetic moment states, right? And now let's make further experiment. Let's consider the case where we're going to use 2 splitters. So we are going to put in the first one magnetic field as we did before, right? In this one we put magnetic field in the z direction. So the gradient of magnetic field here increases in the z direction. Okay. And in this case, we again put magnetic field in the z direction. But we are going to stop the lower part. We are going to stop, put a cover here. Okay. We are only going to let through the positive, the upper, the guys who go up. So what happens in the experiment is that the guys who go up continue going up. Okay. If you put magnetic field both in z directions. So again, this is bz, this is gradient in bz, right? But the question is, what if we point the magnetic field of the 2 splitters into different directions? So if you put, for example, magnetic field in the z direction for the first splitter, so this guy will split into going up and down, right? Let's say I put here magnetic field in the z direction. But then here I put magnetic field in the y direction. And I stop the lower guys, that lower atoms that left the first splitter. So it will split, go up, and it will split again into 2 rays. It will go one down and one up and one down. Okay, let's label this. By the way, I'm introducing here already these notations, plus and minus, right? So plus and minus, when it goes from magnetic field in the z direction, you get this plus. You get this little z here on the corner. Okay. All right. Is it therefore correct to say that half of the atoms that entered the second apparatus have components plus z and plus y, and the other half plus z and plus and minus y? The question is it correct to say that the guys who will go out of here, let's say half of the atoms here, when it's split, right, into these 2 guys, half of the atoms was like this, and half of the atoms was like this, these atoms? The answer is no. The answer is no, and we can prove by doing again the same experiment, but putting in the last time splitter in the z direction again. So here we put the gradient in the z direction. Here we put the gradient in the y direction. Here we put again the gradient in the z direction. So what happens is, in the last one, it goes out again, splitting half and half, up and down. So it means that no. Uh, if you put, again, select only the positive states here, if you redo the experiment, right? You put through the Z splitter, stop the guys who goes down, select only positive signs, put again in another splitter, but in the Y direction. Select only the guys who goes, let's say, to the left. I don't know if this is y direction. Let's say this guy goes to the left, right? If I select these guys, make again splitting on the Z direction, what happens is that 50% will go up and 50% will go down. This is very, very strange character of quantum mechanics. And this is an impressive illustration of a fundamental property of quantum mechanics. Okay? The final state of the system depends only on the state of the atoms that enter the last Stern-Gerlach apparatus and on the action of these apparatus. There is no memory of the previous history of the system. In short, the second apparatus singles out the state plus y, and in so doing, completely destroys any information about the value of sz. So once you split them again, you realize the experiment. Should they go left or right? Once you split them just in the guys who took the left, and you split now in the z direction, then you only get 50% up, 50% down again. So it's like a pure quantum state again, without splitting. Okay, guys, this is 12:30. We have to have a break now. Okay. And then when we go back, we will continue with the Young's double slit experiment. Okay. Instead, just one slit. Let's cover this hole here, so nothing can cross from here. Only at this part. This part is open, right? So the wave, let's say you have a wave front coming in this way, right? When this wave touches the wall, the wave will only go through the slit, right? So what happens is that this slit will do some spherical wave like this. And if you put a wall here, if you put a wall, what you're going to notice is that it will have a maxima around the position of this hole. And vice versa, if you do the opposite, right? So if you close this part of the wall and let just the wave front go here and cross here. So again, it will be this circular pattern until it touches this wall. When it touches this wall, you will see that the maximum happens in front of this stuff. But now, if you let the two waves go through both slits, so both slits are open, and the wave front goes here, right? The wave front goes here, and it will pass, and you will have some circular stuff going here, and circular stuff going here. What happens is that they will start interacting. So we will have a combination of maxima and minima from these waves, and they will interfere with each other, you know. So the point is that when you see what happens in the wall here, it will have this non-trivial behavior. It will be this very complicated series of maxima and minima. So it will not be just the immediate sum, but it will be this combination of maxima and minima, right? Okay, this is the interference. But what Young did, he did this experiment with light also. And at that time, he was from 19th century, something like that. The thing is that in the second half of 19th century, uh, after, by the way, I think I had, but I don't have it here to show. Huh? Let me see if I can find really quick, because I love this. I love this figure. If you go to Google Maps, let me show you guys. If you go to Google Maps and zoom in Olinda, Olinda is a city in the coast of Brazil. Okay, it's a very beautiful city. Let's go for this map. There is some constructions they did there. And I only saw this in Olinda, but maybe in some other places there is also this thing. Let me see. This is the high tide. Did they change this stuff? You see, there are waves on the sea. And yeah, here, look at this. Look at this. So this is construction from the government because the sea is rising, you know? And they put a lot of rocks. So what happens is they let slits on these rocks. And then the waves from the ocean go here. And when they cross the slits, they get this circular shape. And then they start digging on the beach, you know? So if they didn't put these walls, the waves would just dig and dig and dig and go over the city, you know? And then they decided to put these walls of bricks. And then what happens is it this stuff that I was talking about, this is just to show you that this is not only theoretician, this is real in practice. So this stuff is everywhere, you know? You can here you can even see these patterns. So this wave came, crossed by the slit, and then you see that the waves get this circular shape. So before here it was just plain waves, this was just a line of waves coming, and then after they go through these slits, they get these circular shapes. This is everywhere there. By the way, maybe we get this interference pattern. I didn't think about this, because here we have two slits next to each other, and maybe we have a maxima and minima here. What do you guys think? This is already the road, so they protect the road, and this is too far away. Not there yet. Let's wait until they dig here and see what will happen, right? Okay. Anyways, Olinda, Olinda. Yes, I used to live very next to Olinda. I used to live in Recife. This is the coast of Brazil. I used to live here. I did my university. I did everything here in the city. It's very beautiful. It has the biggest carnival in the world. Okay, but enough of that. Let's go back. I'm sorry, guys. I got excited. So the point is that in the second half of the 19th century, after synthesis of Maxwell, Maxwell derived the Maxwell equation, right? It became clear that light is an electromagnetic wave. I'm going to try to show here in simple ways. Of course, nobody needs to be already professional in this. I will just show quickly what this waves means. But in this framework of his equations, he found that there was a characteristic speed for waves in vacuum. And this speed is 3 times 10 to power 8 meters per second, which is exactly, when they measured, was exactly the speed of light, you know? So this is the results of Maxwell. I will try to quickly show here. So the point is that Maxwell himself discovered that electromagnetic field, so electric field, magnetic field in vacuum, they obey the wave equation. So wave equation, what is this equation? It's Laplacian of U. Let's say U can be electric field or magnetic field. Laplacian of some quantity is equal to 1 over c squared, 1 over the wave speed, times second derivative in U again. So it's this equation has exponents 2 and 2. So for Valeria, this doesn't have exponent 1 like Ginzburg-Landau. So it's different class of equations. But anyway, what he did, he took the Ampere law and Faraday's law, okay, and he manipulated these laws to get the wave equations for electromagnetic field. So whoever is curious, on this side, on this equation here, we have Ampere law. So rotor of B is equal to this term, time derivative in electric field. And then you can take the rotor in both sides. So you take rotor here, take rotor here, okay? And then when you apply some vector identities, what you get is that Laplacian of B is equal to this number, epsilon 0 mu 0. So this is electric permeability of vacuum, and this is magnetic susceptibility of vacuum. It's constant here. If you make C equals epsilon 0 mu 0 to power minus 1/2, you will get exactly wave equation, right? So you manipulate one of the Maxwell's equation and get that magnetic field in vacuum follows the wave equation. Same thing if you take Faraday's law. Faraday's law is rotor of E equals minus dB dt, the time derivative of magnetic field. So what you do, you take rotor on both sides. When you take rotor on both sides, you simplify your equation more or less. And what you get is that Laplacian of electric field equals also this factor, right? Epsilon 0 mu 0, which will be speed of light. So it also, Faraday's law also gives equation for the electric field. So both electric field and magnetic field in vacuum, they follow wave equations. And by the way, whoever is interested also in solutions to electric field and magnetic field, the basic solutions, you can construct general solutions in terms of these solutions, is of the form some vector, some constant vector, times exponential of I k times x minus frequency. So k, this is wave number, and nu, this is frequency, times the time. Okay, so this kind, it follows this kind of solutions, these equations for electric field and magnetic field as well. And basically this means that because we have exponential of I times something, I times kx, for example, let's make time equal to 0. And this will be exponential to I kx. So this will be just sines and cosines. And if you take the real part, because you want to work with real variables, if you take the real part, this will be pretty much cosine of kx. It means that you have a wave there, you know. So also in time, right? So if you make x equal to 0 and change in time, you will see that here will also appear cosine of frequency times time. So it gives that electromagnetic waves, they are waves not follow harmonic oscillator, right? Sines and cosines. These are the solutions to these equations. Okay. And this was the big discovery of Maxwell. At that time was no Nobel Prize, but he should get Nobel Prize for this if he was alive, because he confirmed that light follows wave mechanics in vacuum. And later, after Maxwell, what happened was there was also many experiments, for example, from Einstein and from Planck. This was beginning of quantum theory, that proved that light also follows particle mechanics, not wave mechanics. So it's very strange. For example, the distribution of radiation emitted by the black body. So the black body radiation, this is already very complicated problem from physics that I would have to do very long derivations with this. Okay, so I will not go into this stuff. But the point is that Planck, Max Planck, German guy, he could only explain some measurements that they did and some spectrum of the black body radiation if he did the quantization of the oscillators in this black body. So basically, what was the experiment? So let's say you have some body, as the name says, a black body. It's not the body of a black person, but it's a body that only absorbs energy. So always when the light goes here, one cavity here, that this can let light out. Okay, so what happens is what this Planck was calculating is that the radiation inside here somehow it should be connected to the particles, the oscillators in the body, right? So this radiation would be being absorbed and emitted inside here, and would be all the time reflected, absorbed, reflected, and so on, right? Eventually, it would go out here by this hole, and then he would put a detector here. He would put a detector and measure what was the radiation there. And in theory, if everything was continuous, the radiation should be something like this. But what they were actually measuring is that radiation did something like this, but then decayed. And then, anyway, it's a lot of details. I will not go into this stuff. But the point is that he could only explain this if he quantized the oscillation of the particles inside the black body. So this was beginning of quantum theory with Max Planck. And in 1905, Einstein, when he was describing the photoelectric effect, he also tried the particle theory. So he assumed, he admitted that lights consist of particles, beam of particles called photons. So each possessing energy frequency times Planck's constant, and momentum was uh, frequency times Planck constant divided by speed of light. And this was the point, because in principle, your energy, if the energy of your photons is age times frequency could have in principle any value. This was a continuous, right? But because of quantization, because the oscillators itself inside the oven, inside the black body, they had quantized spectrum. So the point is that these photons were produced with quantized frequencies. So there were discrete levels of frequency. It was not any frequency you want. So this was the revolution. This was the problem of quantum theory. And this is how Einstein got his Nobel Prize, by the way. He got because of the explanation of the photoelectric effect. And this was beginning of all these particles, photons, gravitons, magnons, all this stuff began in this thing. Yeah. So both Maxwell's theory, which described light as an electromagnetic wave, and Einstein's theory, which described light as a beam of elementary particles called photons, received broad experimental confirmation. So both of them, if you do some kind of experiment, you get one behavior. If you do another kind of experiment, you get another behavior. So this again raised the question as to the particle of wave-like nature of light, right? So the crucial relevance of Young's double-slit experiment lies in the fact that a complete description can be obtained only by accepting simultaneously both the wave and particle aspects of light, the wave-particle duality, right? So somehow the conclusion of his experiments, we are going to check now, is that you should have both happening at the same time. So again, let's go for the experiment of waves with light, right? So light intensity E at a point X on the screen is proportional to the square modulus of the electric field at the same point, right? Let's call this E1 and E2. The electric field produced at X by beams passing through slits O1 and O2 respectively. So again, you see that we have I1 proportional to E1 squared. So this is I1, right? So the intensity will be proportional to modulus squared of electric field, gives this wave profile like this. And then I2 is proportional to electric field squared again. So it will produce this second profile if they were isolated from each other. If you measure this doing closing one of the boundaries, right? If you close this or this, right? If you open both slits, what happens is that now your electric field, because the Maxwell equations, they are linear, that will be superposition. So the electric fields will be the sum of electric fields. But now the intensity is proportional to electric field squared. So what happened with electric field squared? This will be E1 plus E2 squared, which is just different. So it means that E of X is different from E1, I1 plus I2 of X. So it means that it will not be just be the sum of these two waves, and you should get this profile like this. No, should not be like this. What you will actually get is a profile that looks like this. It will be this very complicated profile. Okay. Questions here? Is this too far, too fast? What do you guys feel? Is it okay? I'm a bit concerned that it's too advanced stuff, and maybe it's hard to understand. I don't know. Maybe I'm explaining this bad. I don't know. Yeah. So this is in agreement with the predictions of the wave theory of light. But question: what happens if light intensity is reduced so that the source only emits photons one by one? So now we are going to the limit. Okay, we see that the wave theory works, but let's go to the very limited rate of photons in such a way that if I emit just one photon every measurement, I send one photon a lot of time, then another photon, then what happens? That there should be no interference there. It's like I closed one of the slits, because now if I have only one photon, what happens is that the photon should go through here and produce this pattern, right? Or I could close this guy, and then the photon should go through here and produce this pattern. If I have only one photon, if the light would be made of particles, right? So what would happen if I emit photons one by one? If the exposure time is sufficiently long that the photographic plate can capture many photons, the interference fringes do appear again, So what is the catch here? The catch here is that in principle, if you send just one photon, it should just produce this line. But what will happen if I open both slits? The probability of the photon going into one slit, probability going through another slit, will interact with each other this quantum way, because the world is quantum now, right? It will interact with each other, and actually the way it will behave will be like this, which goes back to the wave theory. So because you send just one particle, and this is behaving like a wave, it will have these fringes. This is the strange, non-trivial thing of quantum theory. Even one particle can mess up everything. right? And again, light again went to this state where you don't know exactly if this is a particle, if this is wave. Okay, guys, let me check here how much time I have. I have a lot of time. 50 minutes is okay. Yeah. Questions? Um, since we have time, I think we can. Everything clear? Okay. Yeah. So, therefore, the photons, as they arrive, build up the interference fringes, and these fringes can be explained by a wave interpretation instead of particle interpretation of light. Even though it's only one particle, this behaves like a wave, you know. It's very strange. This means that we cannot explain the whole of the experimental results using either the prediction from the particle theory alone or those from the wave theory alone. Both particle and wave-like nature of light are present. Okay. These results force us to revise some of the fundamental concepts of classical physics. The fact that interference fringes are observed if and only if we do not know through which slit each photon passes forces us to give up the concept of trajectory. And we cannot predict this position, but only give the probability P of X that a photon will strike the screen at point X. So intensity there in this wave drawing, the intensity here will be measured as probability of a photon hitting the wave, as it should be, right? It's logical. Okay, and now the discussion will be how to use all these concepts. I think it's pretty clear now, because the point is that we used, so first thing was spin of the electrons, and the probability of going through one slit or another slit. So basically we were constructing the wave function, the probabilities of going through one path or another path, right? Okay, now we start with qubit. So a classical bit is a system that exists in two distinct states. We saw this last time, which are used to represent 0 and 1, right? Single binary digit. In contrast, a quantum bit, qubit, is a two-level quantum system described by a two-dimensional complex Hilbert space. Hilbert space here means that there will be a set of functions, and with these functions, you are going to describe the probabilities of your quantum system. So I'm not going to go into detail about Hilbert space because this is too technical, it's too mathematical, and I don't think we gain much from this stuff. But maybe next seminar I might talk about simply the properties of the wave function, like normalization, modulus psi squared equal to 1, and so on. I might discuss this stuff. Okay, but for now, let's just see that in this space, one may choose a pair of normalized and mutually orthogonal quantum states. So what this means, normalized, again, as I told, right? So normalized means that it's vectors of norm 1. So what means vectors of norm 1? Means that if I make, let's say, norm of a vector is equal to 1. What is the norm of the vector? Vector in a product with the vector, right? Means that this guy is 1. In this notation here, this is called Dirac notation. So Dirac notation, you guys probably saw this before. In Dirac notation, I can do something like this. I can do 0, right? This is the adjoint vector. So if this guy is a vector, this is the adjoint vector. And the inner product you build with the vector and its adjoint. Okay, so you can make something like this. And this will become the inner product of this vector. Okay, and as you can see, the norm of these guys, this guy here, obviously this is 1 because this is x, or first entry squared plus second entry squared. This is 1, right? So this is how you do inner product and so on. Same thing with this guy. You can show that inner product of this guy equal to 1 also. This is just 0 squared plus 1 squared, right? These two components, which gives you 1. And these two vectors, they represent values 0 and 1 of a classical bit. So we are going to construct the quantum bit starting also from this binary definition, because as we saw before, in a quantum system, there is ways that you can define, there are ways to define two distinct quantum states, and that's it. No other quantum states appear. For example, in the Stern-Gerlach experiment, so if you put in the beginning some beam of atoms there um, going through this gradient of magnetic field, what will happen? This beam of atoms will be split into two states, right? And we call this the plus and the minus, right? But at the same moment, this could be the zeros and ones, right? We could just say this will be 1 and this will be 0, something like this. So in a sense, we could say that here I send you something, I send you a bit, and what you did with this splitter here, you splitted your atoms that has values of spin plus and of spin minus. So it means that if you send individual atoms one by one, and they will have chance of being in the state 1, or they will have chance to be in the state 0. So basically, this is how I prepare a quantum bit. How I prepare a quantum bit, I will have, for example, a source of many atoms here, hot atoms of silver, for example. And when I put this beam of atoms, they can have, in principle, they can have any value of spin, plus or minus, right? Okay. This is how we will define these bits. These two states form a computational basis from the superposition principle. Any state of qubit may be written as psi. So this, let's say this is an arbitrary state. This will be defined by alpha and beta coefficients. Okay, so I will again going back to Hilbert space, but you don't need to know exactly about the Hilbert space. You just need to know about vector space. You know that in vector space you have this basis, the base for a vector space. So what I mean here is that if you have a 2x2 two-dimensional space, right? You need a base with two vectors. So since we are dealing with two-dimensional space with this base 2 like this, it means that you are able to build any state just taking any linear combination of these two vectors, zeros and ones. And this which linear combination in particular it is defined by these coefficients alpha and beta. Okay, so the amplitudes alpha and beta, they are complex numbers in principle, but they are constrained by the normalization condition, alpha squared plus beta squared equal to 1, right? So everybody here, I think, knows how to take models of complex number, but I probably don't need to explain, right? So it's just if you have a real number like real part plus e times imaginary part, right? So the modulus of that, the norm of the real number, will be r squared plus imaginary part squared. All right. Uh, Depending on these coefficients, I can build any arbitrary state psi. Okay. So since state vectors are defined only up to a global phase of no physical significance, one may choose a real and positive, except for the basis state 1, in which alpha equal to 0, and one may take beta equal 1 real. What I mean by this? What I mean by this is that you are at some point you are going to want to measure, for example, modulus of psi squared, because this guy has modulus 1. This guy should be normalized, right? So because this guy is normalized, what I mean is that you are going to do this inner product. You are going to do psi, inner product, psi. So as I told before, I'm showing this in detail because there's also a little bit of review. You guys can, maybe if there is someone who is not fully clear on this stuff, if you guys have difficulties, maybe you can send me some message, and next seminar I will make a review about this stuff. Okay, but anyway, how to do modulus psi squared? What we are going to do, again, we are going to take the adjoint of this guy. So this will be alpha star 0 plus beta star 1 in a product with alpha times 0 plus beta times 1, right? So what we have here, is that uh, we are going to use this distributive property. So this guy times this guy will be modulus of alpha squared. Um, this guy times this guy is 0 because they are orthogonal. This is a base, linearly independent base. So it means that the inner product between 0 and 1, it's equal to 0, and vice versa. The inner product 1 to 0, this is 0. So the point here is that this product will be 0, this product will also be 0, and this product will be modulus of beta squared, right? And we know that this guy has to be 1 for normalizing the wave function, right? So it means that we should constrain alpha and beta to only this limitation. So modulus alpha squared plus modulus beta squared equal to 1, right? Okay, so since, did I miss? No. Since state vectors are defined, okay, this I read already. Then the generic state of a qubit may be written as, this is the tricky part. So before we had alpha and beta, right? This is alpha and this is beta. And what I said here is that we can define the phase of this complex number alpha, because we have this freedom of choosing these coefficients. The only constraint, again, the only constraint is that modulus of alpha squared plus modulus of beta squared equal to 1. What we can do is that we can define that the phase of alpha is 0. So alpha will just be a real number. So defining that alpha is a real number, then the difference of phase between alpha and beta will be this coefficient, e to I phi. Okay? And then now, so alpha is the phase of this complex number is 0. So what happens is that this becomes just alpha squared. This now is a real number. So real number squared, right? We get alpha squared. And modulus of beta squared, what happens? What happens is that modulus of I phi, is this complex number has modulus 1, and this will be just like this, alpha squared plus beta squared equal to 1. Now this, I'm summing two real numbers. By the way, wait. Let's not exactly like this. Uh, let's define beta bar as E2 minus I5 times beta. So what will happen? What will happen is that when I kill the phase of beta, when I put minus I5 times beta, this guy will disappear, right? And again, the beta we can substitute for beta equals E2I5 times beta bar, right? Then we can throw here and see that because this guy has modulus 1, we can get rid of this, and then this will be just beta bar squared. This will be, now this will be summing two real numbers. Summing two real numbers. This looks like the fundamental theorem of trigonometry, right? So if you guys remember, sine of angle squared, let's use another letter, right? So let's say sine of gamma, some angle gamma squared, plus sine, plus cosine of some angle gamma squared. This is always equal to 1, right? So we can just name alpha equals sine and beta equals cosine, or vice versa. We can name beta cosine and alpha sine, something like this. Bottom line is that what we are going to have is we can define, this is useful for further calculations, but we can define gamma as theta over 2. And then what you have exactly the relations we have here. So this is pretty much how you express this vector here in terms of alpha and beta, but simplifying alpha into a real number, and beta is a complex number like this. Okay, and then using again this vector notation, this guy is 1 0 and this vector is 0 1, right? So this will be cosine over 2 in the top position, and this will be e to I5 sine of theta over 2 in the lower, right? In the lower position. And in this definition, you can define theta from 0 to pi because of periodicity in cosine, right? And sine. And you can use phi from 0 to 2 pi. So basically, you defined a sphere, because if you remember, I will mention this sphere soon. Okay, let's move on. So unlike the classical bit, which can only be set equal to 0 or 1, the qubit resides in a vector space parameterized by the continuous variables alpha and beta, right? It can go little by little from 0 to 1. Thus, a continuum of states is allowed in this situation. It can be not only or 0 or 1, but it can be a superposition of states, right? And a continuum of states is allowed in this situation. So this contradicts our classical way of thinking. According to our intuition, a system with two states can only be in one state or another. But in this case, you can prepare your wave function as a superposition of states, right? At this stage, one might be tempted to say that a single qubit could be used to store an infinite amount of information. But actually, we must in general provide infinitely many bits to specify complex number alpha and beta. Yeah, so the point is that with alpha and beta, you can map this to infinitely many bits. So this is already showing the power of quantum computation. You know, with one quantum bit, one qubit, you can already map this into many bits, right? But however, there's a catch. To extract this information, we must perform a measurement. And quantum mechanics tells us that from measurement on the state plus minus of a qubit, we obtain only a single bit of information, plus or minus. So the point is, okay, you can store a lot of information in your qubit, but the point is, how are you going to get this information out of this qubit at the same moment? You know, this is a very big topic in research right now. I have a friend even that works with this, and it's not simple. It's not very simple. There are limitations to the amount of information that you can extract from a quantum system. Okay, everything clear, guys? If you have some questions, okay, you can always stop me. All right. So two-level quantum system can be used in practice as a qubit if it is possible to manipulate it as follows. So one, it can be prepared in some well-defined state, for example, in state 0. Sorry, there's a typo there, which can call the fiducial state of the qubit. What this means, right? So it means that in principle, I can prepare this beam of atoms, again, this 10 galaxy experiment, right? So I can send this beam of atoms into the splitter with magnetic field, and this beam will split state up and state down. So what do? I can put a wall stopping one of these guys, and I can select only this guy. For example, let's call this guy 1, with the spin Sz equals h bar over 2. So I can prepare my system already in this state, or I can call this 0. I don't know how he want. I want here define 0. So this fiduciary state, you can prepare your system in this state, this quantum state that you know. Any state of the qubit can be transformed into another state. Such transformations are carried out by means of unitary transformation, as well we'll see further in the next seminar. So in the next seminar, we are going to go through this, how to do these transformations and put the quantum system from one state into another state. But basically, what I mean here is that repeating that part of this 10 galaxy experiment, so you can have a splitter here into the x direction. So let's see BZ in the x direction. And then I can put, again, another splitter into the y direction. I can put magnetic field in the y direction. So if I put magnetic field into the y direction, what will happen is that these two guys now will go again, one to the left, one to the right? And then what we have again? We have made a transformation into another states. So this side here will be Sy equals h bar over 2, right? And this lower one here will be Sy equals h bar minus h bar over 2. Minus h bar over 2. So what I did here is that I had the system in this state, and what I did this transformation. As we will see soon, this is some kind of unitary transformation, what we call unitary transformation, and then it becomes this up and down, or left and right states in the case of the y direction, right? And then I will prepare the system into these two different states now, which I can do again and again and again and go splitting this. The problem is one of the limitations, if you put a beam here, there is a finite number of atoms. So if you put here in the beginning n atoms, when they go out here will be n over 2 in this direction, n over 2 in this direction. Let's say if they are randomly driven. Here, the same thing. Here will be n over 4, right? In this direction, n over 4 in this direction. So this means that there is exponential decay of number of atoms. And then your experiment will become harder and harder until you get to the point where you don't have atoms, just don't have sufficient atoms to see, to measure this stuff. So in principle, yeah, in your qubit, you can store a lot of information because this phase, it has two angles there, right? You have alpha and beta as we know. But the point is, every time you make a measurement, every time you make a transformation, you take a transformation of your system. And this we lose with this, right? Again, talking about these limitations, right, of this computation operations. Okay. The Hermitian operator associated with measurement is the Pauli operator sigma z, which has eigenstates 0 and 1. Oh, sorry, here is also another typo. 0 and 1. Okay. So what I mean by Hermitian operator, probably maybe you guys already saw this stuff, but operator in linear algebra, this is a matrix, right? So let's say this is A, B, C, D. So Hermitian operator is the operator that, let's call this H, right? So Hermitian operator means that H equals H dagger. What is H dagger? It's a transpose matrix and you take complex conjugate. So H dagger or Hermitian conjugate. The Hermitian conjugate is A star, complex conjugate of A, B star, C star, D star. Okay. So what I did, I took the transpose, I exchanged these two terms, and then I took the star in this guy. So the Hermitian operator associated with this measurement is the Pauli operator sigma z. What I mean here by measurement also, what I mean by measurement is exactly this thing that I was showing. Oh, I deleted this thing I was showing before. When you make this measurement with the magnetic field, for example, you will define if some atoms have spin up or if this thing has spin down, if it went up or down, right? In principle, before going through the splitter, you didn't know what was the state of this atom, but then after you go to the splitter, you will measure and see that it went either up or down, okay? And this is given by this Pauli operator sigma z, which has eigen states 0 and 1. So let me write here, I forgot to write that sigma z, this is 1 0 0 minus 1. Maybe some of you guys know these Pauli matrices. So this is diagonal matrix, and the diagonal matrix that has these elements here, you can call this the eigenvalues, right? And the eigenvectors of this matrix is very simple. So one is this 0 eigenvector is 1 0, and the other eigenvector you can call 1, which is this guy 0 1. Okay, so this is why he means that which has eigenstates or eigenvalues. This here should be eigenstates 0 and 1. Should be something like this. Sorry for this typo. Thus, if the state of the qubit is described by this vector in this way, so a result of measurement, one obtains 0 or 1 with probabilities p0. Okay, so it's when you making inner product. So you take the component of psi in the z direction. So what we are going to do, we are going to do 0 inner psi and take the modulus squared. This will be probability, is the definition of probability of finding your state in the finding your system in state 0, right? And as we saw before, this will just when you make here 0 like this, with this guy will give 1 the inner product, and with this guy it will give 0 the inner product. So you will just select this guy. So this will give modulus squared of cosine, right? But this is a real number, so you just get cosine squared. And same thing with P1. So probability of finding the system in your state 1 will be take the inner product of your state with the vector 1 and then make modulus squared. So again, when you make the inner product with 1 here, what will happen is inner product with this guy will give 0, and inner product with this guy will give 1. And modulus squared of this guy is 1. This is e to y p, right? So this will just give this value. Sine, this will just give sine squared of theta over 2. Okay. Now, if you, so I previously I mentioned, but now we are going through that. The point is that describing your quantum system in terms of these angles theta and phi, it's the same thing of having a sphere. A sphere, probably most of you guys worked with spherical coordinates, right? So spherical coordinates, it's a way to define, to describe the 3D world in Cartesian coordinates. So in Cartesian coordinates, you have x, y, and z, right? So what we have here? What we have here is that this is my state psi. If I have, again, psi as a linear combination using alpha 0 plus beta times 1, right? If I, in general, it's like this, but if I describe using cosines and sine, so cosine over 2, 0 plus e to y phi sine of theta over 2, 1. If I use like this, I get exactly spherical coordinates. So it means that I can think of my quantum state as a vector in a sphere with radius 1. Okay, so having radius 1 means that modulus of alpha squared plus modulus of beta squared equals 1. So this is the famous Bloch sphere. And if you represent in terms of angles, these angles will be exactly um, the angles in the spherical coordinates. Okay. All right. So Pauli operators. Again, I showed you guys this operator, sigma z, okay, and computational basis, right? I mean that 0 and 1, right? So in this base, the Pauli operators get this form: sigma x like this, sigma y like this, sigma z like this. I will explain what this means. Okay, what this means? What this means is that when you apply these matrices in the quantum state psi, so when you apply sigma x on psi, you get this vector. Look at sigma x. It has this one here in the off diagonal and one here in the off diagonal. In the main diagonal, it's 0. So what it's going to do, this matrix, it will just exchange x for y. So the component here in y now will be to e to y phi sine of theta over 2, and will be cosine of theta over 2 for 1. Right? So we pretty much just exchange these two coefficients. That's the action of sigma x. I promise you that it will be clear what I mean, what means sigma x, sigma y, sigma z. Okay. So sigma y acting on psi, it gives exactly, look at sigma y here, it's minus I times this guy, right? So what you go in the reverses, so you get exactly same thing, so but with minus I in front of, with I in front. It will exchange the coefficients cosine and sine and put this e to y phi here in this first guy. Then the final operator, again, this is z component of the Pauli matrix. It will just give plus this guy minus this guy. That's the only effect of the z Pauli matrix. it will be change sign of the second component. Okay, why am I talking about these operators? Is that now when you make the contraction, when you make inner product with your state, when you make psi, sigma, psi, what you're going to have? What you're going to have is, again, these sines and cosines, right? You remember this representation? Let me write here on top. So psi, this is cosine theta over 2 times 0 plus e to I phi sine of theta over 2, 1, right? This is in general this guy. So when I do this sandwich, as we saw before, we exchange the coefficients. And because we exchange the coefficients, when you sum now, after you make the inner product between these two guys, you will get just sine theta cosine phi, which in spherical coordinates, this gives you x. So it means that going back to the Bloch sphere, when you make this sandwich psi sigma x psi, you get the x component of your wave function. So if your wave function is here, is this vector here, what you got? You got the x component of this wave function. So this is the projection into the horizontal plane, and this is the projection into the x direction. So basically you get the x component, right? If this was a 3D world with in a sphere of radius 1, actually a 2D world. If this was a 2D world spherical, you would get this x component of your vector. Okay? Same thing will be for the y component. So the y component here, when you make this sandwich in between these two guys, it will result in sine of theta, sine of phi, which will give just y. So again, same thing, right? You in the Bloch sphere, what you get? You get the projection, again, when you make psi sigma y psi, when you make this, you will get basically y. So you will get the y component of your wave function. Okay, and same thing for the z direction. In the z direction, when you apply, you will get pretty much the z component of this wave function here into the Bloch sphere. Okay? Yeah. So, questions, guys? Everything okay, right? It's a bit tricky, but in the end, it's simple. If you already worked a little bit with this with previous guys, it's kind of intuitive. Okay, so the coordinates x, y, z can be obtained with arbitrary accuracy by means of standard projective measurements on the computational basis. That is measuring sigma z. So how do we measure sigma z? How do we see the z coordinate of our wave function? Making p0 minus p1. Probability of being in the state 0 minus probability of being in the state 1. Right? So this can go from -1 until +1. This is continuous value that can go from -1 to +1, depends only on theta. By the way, this is mistake here. So it's over 2 here, right? So then cosine squared minus sine squared gives the cosine of the double. So it gives this guy. Okay, sorry for the typo. But the point is that measuring z gives you the difference of finding these two stuff, right? So the coordinate z is given by the difference of the probabilities to obtain outcomes 0 or 1 for a measurement of sigma z, okay? If we have at our disposal a large number n of systems identically prepared in the state psi, we can infer. Infer means that we will collect a lot of statistics, a lot of measurements, and then we will make inference. So eventually, after a lot of measurements, our measured results will give what are the probabilities. Okay, and this will be n0 over n minus n1 over n, where n0 and n1 count the number of outcomes in 0 or in 1. Again, I will repeat again because I want to be very repetitive itself until it's very clear. So let's say you can throw a lot of atoms, you can throw a lot of, I don't know, photons, whatever. Let's use the Stern-Gerlach again. Okay, so let's say you throw a lot of individual atoms, put this through the splitter magnetic field in the z direction, and you will measure some atoms went up, some atoms went down, right? So the number, he's basically telling here that the number of atoms that went down divided by the total number is the probability P0, right? And vice versa. The number of atoms counted up divided by the total number, this will be P1, okay? And then when I do P0 minus P1, this will be the Z component of my wave function, of my state function, my quantum state, in the Bloch sphere. Okay? Okay. So basically what I meant was that depending on the measurements of the probabilities, you can go with the Z component up to here, which means you prepare the system only on the up, going up in the Stern-Gerlach experiment. It can go down to -1, P0 minus P1, right? P0 minus P1. When it's -1, it means that the Z component is -1. It means that you prepare the system, all of these guys in the lower direction. It means that, for example, when you put through the splitter, these guys will go both ways, but you cover one of the sides with a wall, and then you prepare the system in this state. So you can say that the state in this system here, where sz equals minus h bar over 2, you can say that this system here is already prepared in this part down here. If someone else makes these measurements, very many measurements of the spin of these guys, let's say there's a counter here of the direction of the spin, this guy will be able to detect that all of them, they have spin down. Okay, this is Bloch sphere, sphere. Let's go further. The coordinates x and y can be obtained. So we talked about P0 minus P1 is the z component, right? The coordinates x and y can be obtained by using the possibility to operate a unitary transformation on the qubit. So this unitary transformation, what is unitary transformation? Unitary transformation means that U equals wait, U transposed equals U to minus 1. Okay? Or U dagger, as you wish. Okay, here can be also U dagger equals U to minus 1. This is what I mean by unitary transformation. But from linear algebra, we studied, right? In linear algebra, we study unitary transformation. It just means that if I make the product of these two matrices, 1 over square root of 2 of this matrix times the transpose, I will have the diagonal matrix. I don't think I need to do, right? But it's not hard. If you want to verify, you can do the 1 over square root of 2, 1 minus 1, 1, 1, times 1 over square root of 2, 1, 1, minus 1, 1. If you make this product, you will see that you have the identity, 1, 0, 0, 1. Okay? So if you choose this unitary transformation here and apply this to state psi, we get the state psi1 equals u1 times psi. Okay, let's define the state like this, right? This is definition. A projective measurement in the computational basis then gives outcome 0 or 1 with probabilities p01, p11. Let's study this. Wait, how do I do here? Yeah. Again, let's go for psi state. I wanted to do this here. Cosine of theta over 2 times 0 plus e to y phi sine of theta over 2, 1. So when I apply u1 times this guy, what is going to do? u1 times psi. This will be 1 over square root of 2, right? And this will be cosine 1 and 1, right? So this will be cosine theta over 2, 0 plus repeating, just repeating, e to y phi sine theta over 2, 1. This is first row. I better even use the other notation. Let's use the 0, 1, 1, 0. Better like this. Sorry, guys. 1 over square root of 2. 1 minus 1. I think it will be easier like this. Times the notation like this. Cosine of theta over 2. E to y phi sine of theta over 2. So what you should have here is 1 over, let me put on this side so you guys can understand. 1 over square root of 2 times cosine theta over 2 plus e to y phi sine theta over 2. And here will be minus cosine theta over 2 plus e to y phi sine theta over 2. Okay, so this is u times psi. So now to find, for example, this this p01 here, we need to contract this. We need to make inner product with this 0 state. So let's do 0 times u1 psi. This will give 1 over square root of 2. By the way, so 0 is 1, 0, right? So what do? We just select the upper part, right? This 1 over square root of 2 cosine theta over 2 plus e to y phi sine theta over 2. And now you need to take modulus squared. When you calculate modulus squared of this guy, you will get 1/2. Let's put this p0 here below. 1/2 times. It's clear that we'll have this number multiplied by the complex conjugate. Will be cosine theta over 2 plus e to minus I phi sine of theta over 2. So this will be cosine squared theta over 2. How do I do this quickly? This guy and this guy. Sine theta over 2. Let's do brute force anyway then. So this will be cosine theta over 2 sine theta over 2 times e to minus I phi plus same thing, right? Cosine sine e to I phi. Yes. And then this is modulus conjugate. This will just kill plus sine of sine squared of theta over 2. So this is this guy plus this guy will give 1. This will be 1/2 of 1. And this will be plus this complex conjugate. This number plus its complex conjugate. You just get twice the cosine, right? Cosine phi, cosine theta over 2, sine theta over 2. Okay, so this is this probability P0, 1 after unitary transformation. Maybe we can leave even as homework to do this, because this is already pain in the ass, but can be homework, home assignment, to do P0 and P1, these calculations, who is P0 and P1. Okay, this will be important in the next seminar when we start studying quantum gates, when you go for quantum computation. Okay, in the same way we can do this guy here, U2, like this, and then obtain again state psi2, U2 times psi, and therefore when you calculate P0 minus P1, you will get y direction. So this was done this here, you would get the x direction. So the result here, I forgot to put this part, huh? But the result here is that if you do P01 minus P11, you would get the z direction, I think. No, the x direction. Here you get the x component. On the next, we do this calculation here. I already put the final result, and you get the y component, and then the z component was before, right? This z component here. So what is the main message here? The main message is that depending on the base that we choose, we can make measurements of the component in the Bloch sphere. We can make projections in the z direction. We can make projections in the y direction or in the x direction. So these operators actually mean that we are rotating the Bloch sphere and making measurement. With these unitary operators, we basically can effectively rotate the sphere to the z direction, make the measurement. What is this spin, the connection of the direction of spin there, and then you can always use this as a quantum beat. But the point is that here begins the study of these quantum gates. So basically, through these rotations, we are going to make operations in our quantum beat, and then we will make these measurements. And in the next seminar, the idea will be to again go for these algorithms to make computations with this stuff. Okay. So conclusions. We have seen complexity classes for algorithms. We saw that we rely on complexity of mathematical algorithms in our online security protocols. And we have seen basic phenomenology of quantum systems and introduced fundamental concepts like the qubit, okay, and block sphere. And the idea will be to work with these qubits and do calculations with this stuff. We are going to do quantum computation with these concepts, okay? Thank you for your attention. Questions, comments, anything? Maybe this end here was not very clear. I don't know. There was this little thing I forgot here, but I promise not to do this anymore. I forgot to say that if you do P01 minus, I forgot this stuff. I will include later and send this thing, okay? This will give the y component, the x component of in the block sphere, okay? Questions, guys? No? All right. All right, so thank you. I see you, I think, in 2 weeks now, right? And the home assignment will be to derive this stuff that I forgot. I am clever guy that I will make you guys work. So that will be calculating these components here, okay? So see you and bye-bye.